Hi people, welcome back to the first lesson on stress and strain. There's the note I referred to earlier. And basically stress and strain consists of two formula, just two formula really, two small formula, and we develop them a little further and then we end up using 4 or 5 formula. Okay, so I'm going to explain that first and then do some examples to see how we use them. Right people, definition of stress: when a force is transmitted through a solid body, the body, let me make this bigger, the body tends to undergo a change in shape. This tendency to deform is resisted by the internal resilience or resistance inside the body, and the body is said to be in a state of stress. Okay, so people, so when you're squeezing, say, a column or stretching a column or any member, okay, and you know the force that's being applied to the ends of the member, and you divide it by the area, okay, and then when you do that calculation there, it's called a stress. Okay, so let me just get this right here. The very first big thing in this section is stress, right? So there's it over there. Okay, so stress is equal to force over area. So that's the very first big one I want you to imprint on your brain forever. Okay, stress is equal to force over area. And that symbol there is, do you remember when we did section properties, or whenever we do maths, that there, sigma, okay, we read that as the sum of, okay, that's actually capital sigma and that's small sigma. Okay, so when we use capital sigma in English, we take it to be the sum of, but when you use it like this as a small letter, it's called stress. So stress is equal to force over area. Now people, now when you do these calculations in this section, don't mix up the units. Students do it so often and they get the right numbers, but they get the decimal in the wrong place, which is wrong, of course. Okay, so whenever you get the force, always convert it to newtons. Okay, and whenever you get the force, always convert, sorry, my apologies, when you get the force, always convert it to newtons, and when you get the area, always convert it either to meters squared or millimeters squared, but we are generally going to use millimeters squared for area. It doesn't like the way I'm doing this. Okay, it's millimeters squared. PDF does that. Okay, so therefore people, the units of measurement for stress is newtons per millimeter squared. Newtons per millimeter squared. Doesn't like it. Okay, because force over area, force is newtons, area is millimeter squared, or if you're using meter squared for area, then stress will be newtons per meter squared. Okay, that's the first big formula you need to imprint on your brain forever from this point onwards. Right, I'm going down to the next thing. Okay, the next thing, there's the units over there, newton per millimeter squared or newtons per square meter, as I said. The next thing is strain. Okay, strain. Now, there we go. There's the big formula. There's the symbols. Okay. Delta L over L. I will generally use delta small l. Okay. And that delta L there is increasing length divided by the original length. Okay. And strain there, you can see is another little Greek letter there. Ooh, just hate this. Looks like this. Okay, that's a Greek letter there, and the way to read it in Greek is called epsilon. Okay, but we use it for strain in this chapter. Okay, so strain is equal to the increase in length or the decreasing length. Notice increasing length or decreasing length. Okay, over there. Okay, so if we are stretching a steel member, it will increase. If you are squeezing a column, it will decrease in length. Now people, notice. When we spoke about when we spoke about in the previous lesson in the introduction, when I spoke about when we stretch out a piece of wire, that increase in length is very, very, very small. It's fractions of a millimeter. Okay? Now, if the increase in length is fractions of a millimeter and we divide it by the original length of the column, which is 2 or 3 meters long, so we're taking a very tiny number and we're dividing by a big number. So what's strain going to be like? Is it going to be a big or small number? Strain is going to be a very, very tiny number. It's not going to be a big number. So if you do a strain calculation and you get a big number, you must know immediately you have made a mistake. It's going to be wrong. Okay, because if you take a tiny number and you divide it by a big number, you're going to get a very, very tiny number. Okay, so the next formula there, strain is equal to the changing length divided by the original length. Okay, changing length divided by original length. Now, just watch this. A length, what we measure length in, I'm going to do it on here rather. Okay, do it over here. Changing length, I'm going to use small l, it doesn't matter, over big L. Okay, now the changing length is going to be measured in millimeters. Okay, as I said previously, convert all distances to millimeters, all length to millimeters, and the original length is also in millimeters. Okay, so if a column is given as 2 meters long, that's going to be 2,600 millimeters long. You convert all to millimeters. Now, we're dividing millimeters, we're taking millimeters, and we're dividing by millimeters. So what's going to be the units of measurement for strain? Be very careful. Okay, if we take in 10 millimeters, for example, and I divide it by 2 millimeters, what answer do I get? What's 10 divided by 2? Is 5. Okay. Is 10 millimeters divided by 2 millimeters 5 millimeters? No, it is not 5 millimeters. Okay, you need to get it right, people. Okay. It is just the number 5. Did you get that? So strain is the ratio. Strain is the ratio. I'm making a big fat thing there, a big fat exclamation mark. Strain is the ratio of the changing length over the original length. Okay, whenever you take a unit of measurement and you divide it by the same unit of measurement, you get a ratio. Okay, now let's think if you did maths. Okay, if I say 10x divided by 2x, 10 over 2 is 5, and what's x over x? X over x is 1. What's 5 times 1? It's 5. That is why that answer is 5. And many students think that when we come to strain, that 10 millimeters over 2 millimeters, 5 millimeters. No, it is 5. It just means that this goes into that one there so many times. Okay, so there is no units. There is no units for strain. Okay, right. I'm not going to say that ever again. So reprint it on your brain forever from this point on. So strain is changing length over original length, and it's got no units of measurement. Right? There's it in a picture form. There's our bar. Let's call it a steel bar. Right. This bit here, from there to there, is the original length. And when I stretch it, okay, the changing length, which is very small, divided by the original length, give us a strain. Or if the bar has been compressed, from there to there is the original length, okay, and that little bit that it gets shortened by, if I take the shortened bit and I divide it by the original length, sorry, my tongue is getting twisted here. If I take the shortened dimension and I divide it by the original length, I get a very, very small number. Okay, so that's strain. Right, people? Now, let me just clean the board here for a second. Right, remember, we said there that stress is equal to force over area, and strain is equal to the changing length over the original length. Okay. Now remember when I drew that stress-strain diagram, this one over here. Let me just do this quickly. There's it over there, stress-strain diagram. Now we're concerned with materials up to the limit of proportionality. Okay. And if I take the stress and I divide it by the strain, I get that thing over there. Okay. I get Young's modulus of elasticity. Okay. So Young's modulus of elasticity, E, is equal to stress divided by strain. Okay. And that's the next formula I want you to imprint on your brain at this point onwards forever. Okay. So Young's modulus of elasticity is equal to stress divided by strain. So from force over area, I will get stress, and from changing length over original length, I get strain. And when I take that and I divide by this, I get Young's modulus of elasticity. I'm going to just write it in here. Young's modulus of elasticity. Okay, or E. Big E. Now people, what's the units of measurement for stress? It is newtons per millimeter squared, as we said earlier. What's the units of measurement for strain? It's a ratio, no units. So, what are the units of measurement for Young's modulus of elasticity? It's the same one as stress. It's newtons per millimeters square. Okay, are you getting that? And if I go back to my table of E values, and I make it a bit bigger, like so, there's the units there. Right, the kilo there, what do we call the kilo? The kilo is just a sub-multiple prefix. It just means 1,000 of that, as we did in the first lesson in applied mechanics. Okay, so the units for E is the same as the units for stress. It's either newtons per millimeter squared or kilo newtons per millimeter squared or mega newtons per millimeter squared. Okay, right. Now, let's do a bit of algebra. Now, that there is equal to that. That there is equal to that. So let's put all of this inside here. So therefore, I can say E is equal to force over area divided by delta L over L. Delta L over L. Okay? I'm putting this into the, I'm just doing algebraic substitution. And if I tidy this up, if I do an algebraic, algebraic manipulation, I'm going to get F times L over A times delta L. Let me get that over there. Okay, so therefore E is equal to F times L over A times delta L. Okay, so if we know the load acting on the member, which is the load acting, and we know the original length of the member, okay, and we know the cross-section area of the member, and we know how much the member shortens or gets long under load, we can work at its Young's modulus. But, and that's a but with one T, okay? This formula is seldom used like this because Young's modulus is something that we're always going to know from the table here. That's a known, that's a given, we know that, okay? So from this formula here, the variable that we want to find is almost always going to be the changing length of the member. So, if we make the changing length of the member the subject of the formula, then that there will be equal to F times L over the cross-section area times Young's modulus. Okay, and that's the other one, and that's the fifth formula I want you to put on your brain and remember from this point onwards forever. Okay, so that there is the load acting on the member, either squeezing it or making it longer. That there is the original length of the member in millimeters. That's in newtons. That's the cross-section area of the member in millimeters squared. And that's Young modulus of the member, which I will either give you or you will take from the table here. Okay? And of course, once we work all it out, that there is a distance. So therefore, the units of a measurement for the changing length of the member is always in millimeters. And it's going to be a small amount. It's going to be somewhere between 0 point something up to about 2 or 3 millimeters. Okay? If you get this, if you get the changing length of the member as 5 meters, a member cannot get longer or shorter by 5 meters, people. That's impossible. The member has failed. Okay? That's impossible. So delta L is always going to be a small amount. Okay? Anywhere up to 3, 4, 5 millimeters. Okay? So people, there's the first formula. Stress is equal to force over area. Strain is equal to the changing length over the original length. And E is Young's modulus is equal to stress over strain. And if I put all of this into that, I get this. But generally we use this formula where delta L is the subject of that formula. And delta L is equal to the load acting multiplied by the original length divided by the cross-section area of the member multiplied by Young's modulus for that material. Okay, so people, that's the formula we use in this section here. So I'm going to go ahead and do a few examples to work through. Okay, and people, there's the first example. Example 3.1, it says determine the tensile stress induced in the rod shown in the figure there due to an axial load of 60 kilonewtons. Okay, now people, before I go on with that over there, let me just explain direct and axial quickly. If I go to my note that I gave you, the name of this chapter is where's my the name of the chapter I gave you was called direct stress. Okay, now let me just go down. It's called direct stress. Direct stress, generally the same thing. I'm reading it there. In this chapter only direct stresses are those normal stresses. What does normal means? That means if we have, like in the sketch here, normal just means that if there's a bar, and if there's an imaginary center line running along the center there, okay, and if I apply the load that's acting along that line, okay, along that central imaginary line, if it's a square bar, if it's a round bar, okay, and if I've got a load acting along that line, that means that will be called an axial load. It acts along its axis. And also, when it acts at right angles to the ends of the member, to its cross section, it's called a direct stress. It's undergoing a direct stress. Okay, direct stresses are those normal means at right angles to. Direct stresses are those normal stresses in which the force direction lies parallel to the longitudinal axis of the member. In the case of an axial stress, the force is axially power that is aligned along the longitudinal axis of the member. That means, can you see this force here? It's acting parallel and in line with the long. Now the word long is the shortened form of longitudinal. Okay, so when we say long axis, we actually means the longitudinal axis. So when the force lies along the long axis of the member, we say it's an axial force and it's undergoing a direct stress. So that's what it means. Okay, right, there's the first example. Determine the tensile stress induced. What is the word induced? Induced means to be brought about by as a result of something acting on it. Okay, if there's no load acting on it, the bar will not be undergoing any load. But when the load acts on it, the stresses inside the fibers of the bar will be induced as a result of the tensile forces acting on it. Okay, determine the tensile stress induced in the rod shown in the figure there due to an axial load of 60 kilonewtons. Right, the first thing you always do, people, you always do is state the formula. I give you a mark for it. State the formula, then you will see what you need to look for, and then you see you might need to rearrange the formula, put the values in, and get the answer. Okay, first thing, state the formula. We want stress. So what's the formula for stress? Stress is equal to, I'm going to leave it in the red, shall I? Yes, it's equal to force over area. Okay, what's the force? the force is 60 kilonewtons, or the load acting. And we always convert it to newtons. So that's 60,000 newtons over the area. And we always convert to millimeters squared. It's a round bar. So it's quarter pi d squared, or pi r squared, just as you wish. I use quarter pi d squared when I work it with whole area. It's quarter pi d squared, so it's times 20 squared. Right, you work at the answer and you check that your answer is the same as mine. Right, and what you get, I got 190.99. Okay, nice and easy, isn't it? If you did it as 191.00, that's acceptable. Okay, but I'm gonna make it as 190.99. 190.99. And if you leave with the units, I take off a mark. Okay, we're not making cake. In civil engineers, we must get it right. It's newtons per millimeter squared. Some of you like the other thing with the minus sign. That's also okay. That's fine also. Some people want to like the fancy one like so. That's the same thing. I just do that. Okay. If you wrote it like so, 191.00, don't leave out the notes. We work into two places of the decimal. So that and that is fine. Okay. So therefore, the stresses in the material is 191 newtons per millimeter squared. And what does it mean? It means that if I take a cut straight along there, okay, and I analyze the stresses in the fibers there. When I say fibers, means as thin as your hair, okay. And if we analyze the fibers of the stresses there, it's undergoing 191 newton per millimeter squared. And if I take a cut along there, or anywhere along there, and I analyze the stresses in the fibers there, they will all be 191 newton per millimeter squared, because that's this member is undergoing a direct stress. Okay, right, people. Let's go on to example 2. Right, people, there's the next example. Let me just change it over here. Right. Example 3.2. Determine both the compressive stress in the shaft. Okay, there's a shaft there. It is a square shaft. And the bearing stress at the base of the column, shown in the figure there. So there's a square shaft, and then there's a taper. It gets wider as you go, sitting on the base there. Right. So it says they work out the stress on the plane there, plane XX, which is anywhere along the length of the column, and then work out the stresses on the YY plane there, where this tapered base sits on that base over there. Now people notice the force or the load is the same throughout. The shaft and the column and everything is undergoing a compressive load. Now, here's the area at XX. You'll see it is smaller than the area at YY there. Okay. Do you think the stresses are going to be the same at both planes there, XX and YY? I don't think so. Have a think. The one's going to be smaller, the one's going to be bigger. Or can you predict which is going to be bigger, which is going to be smaller? Alright, let's work it out. Right, so I'm going to say at XX. I'll say at XX. Right, determine the compressive stress. What's the formula for stress? Take the formula. Stress is equal to force over area. I'm going to go across here. Right, what's the load? It's 10. Now be careful, people. What is M? Mega. What does mega mean? A million of. So 10 times 10 to the power 6 newtons over the area. What's the area? Let's leave the area at meters squared. So it's a 0.8 meters squared shaft. So it's 0.8 multiplied by 0.8. Okay. So it's equal to, I think I wonder, let me rather make it millimeters. Let me rather make it millimeters. Okay. Millimeters rather. Right. So that's 800 millimeters. So it's 800 millimeters by 800 millimeters because it's a square. Okay. Right. So it's 10 million newtons divided by 800 millimeters square shaft. Right. So let's do the calculation and check if you see you get the same answer as I do. Right. And what did you get? I got 15.63. 15 point. That's a nasty 5 that is. newtons per millimeter squared. Okay, Newton per millimeter squared. There we go. So the stress anywhere along the plane here, along the shaft, this bit here, okay, of this dimensions, will be that there. Have you thought about what is going to be there? What do you think the stress is going to be along plane YY? Okay, if this is going to get bigger and that's going to get smaller, we expect the answer to be smaller. That's right. So if there's more area, the stress will be reduced on the fibers there. Okay, so I'm going to say at YY, stress is equal to force over area, and the force is 10. If you want to do, you can even do that. It's the same thing, 10 million newtons over the area, and it's 1.5, so that's what's in millimeters, so it's 1,500 millimeters, but it's a square, so it's square is equal to, and we get the answer, it is 10. I'm doing my calculation here, and I get 4.44 newtons per millimeter squared. Okay, so can you see there that the force or the load being carried is the same, but as you make the area bigger, I mean, it makes sense. I mean, if you look at it, it makes mathematical sense. Okay, if you look at this little calculation over here, if that stays the same and that's get bigger, that's ultimately it's going to get smaller. Okay, so that's the stress along the x plane, and that's the stress along the y plane. Okay, people, I will do a few more. A few more examples, and I think I'll do it in the next video. Okay, I'll see you in the next lesson. People, I thought I'll just do another one, okay, before we do another lesson. Right, next one there. Determine the shearing stress induced in the rivet shown in the figure due to a shearing load of 40 kilonewtons. Now, what is a shearing load? Okay, just very briefly. If we have a column, let's say we had a column like so, or a bar, okay, and we squeeze it along like so, we say it's undergoing a compressive load, okay, and if we stretch it out like so, we say it's undergoing a tensile load, okay. Let's say here we have a plate. These are two plates here. One is fixed, it's welded or some particular way. We have another plate here bolted to it. I mean, for example, let's say we have a steel column there, and we have a steel column there, and we have a member there and a member there. Okay, now that joint there, it could be maybe like, say, it could be like a plate. Let's say we have a channel section like so, or an arch section, and we have a plate that comes out of something like so, and we put a bolt in there and a bolt in there. Okay, now if we look edge on, if we look at it edge on like so there, that plate could be this one here, and this angle could be that plate over there. Okay, and that rivet there, well, I don't know if you know what a rivet is, people. A rivet actually is sort of old-fashioned fasteners. Old-fashioned means we don't really use them anymore. Rivets are permanent fasteners, okay? To undo that, you can't undo it, you'll have to drill it out, okay? Today, we use mainly bolts, okay? Bolts and nuts, okay? So, if I look edge on, that plate could be that plate there, and this plate could be this plate over here. And that rivet over there is that rivet over there, okay? So, that rivet prevents this angle here and that plate from moving away from each other like that. That keeps it, it bolts it together. In this case, it's a rivet. Okay. But I notice here, this member is undergoing a compressive or a tensile load. Okay. Now, just over here, can you see the arrows there? Just over there. Okay. That if this plate was pulling upwards and this plate was pulling downwards like it wants to do, okay, then this rivet will fail along there. It will almost cut across its diameter, okay. These two surfaces here, they want to move apart from each other, and we call that a shearing stress, okay. And then let me just take this out quickly here like so. Let me just mention shearing stress somewhere else quickly also. Okay. Let's say we had a beam. Let's say we had a beam like so, and we had a column like so. The beam is loaded up. Okay. What will want to happen? What will want to happen is that this beam will want to break out right over there. Break out right over there. This bit wants to fall through, and those two pieces there will want to stay on there. Okay, so at that plane there and that plane there, the beam is undergoing shearing stresses. Okay, but what we do in real life is we actually put bars in there, steel bars like so, to resist that shearing stresses, so that the beam and the column and the structure stands up nicely for the rest of its working life. Okay, so that kind of stresses induced inside that kind of member there, and those planes there is called shearing stresses. Okay, so that's a little bit about shearing stresses. Right, people, what did I always say there? First thing is state the formula, shearing stress. So stress is equal to force over area. And what's the force? Is 40,000 newtons. You convert it to Newton, like I said. I'm not explaining it anymore. What's the area? It's a 20 millimeter finished diameter. So what's the area? It's quarter pi d squared, which is the same as pi r squared. It's times 20 squared. And you work at the answer, and you see you get the same answer like me. And I got 127.32, which is what you also should have gotten. 127.32 newtons per millimeter squared. Believe it, the units, I take up a mark, and it's not newtons, not meters squared, it's not meters cubed, it's newtons per millimeter squared. Okay. Okay, people, so that's the shearing stress that this rivet will undergo just along that plane over there. They'll tend to want to move over each other and tear apart, undergoing that kind of shear stress there. Okay. Okay, people, I'll see you in the next lesson, where I'll walk through another 2 or 3 examples using stress, strain, Young's modulus, etc. I'll see you then.